Now that we've finished with conservation of momentum, we're going to move on to our next conservation law, the conservation of energy. Energy is conserved. This is a general concept. You've probably heard about this before, but it cannot be created or destroyed. It can change form, it can be transferred, but it cannot be created or destroyed. It is conserved. Another way to think about this is the total energy does not change with time. This is a really big deal in physics, so we're going to spend the next 3 lectures talking about this. Energy cannot be destroyed or created, just changes form. We say it's conserved. This is true for any isolated system. Now just bear in mind it can sometimes be tricky. For instance, you can have an example when I put on the brakes. So if I'm driving in my car has kinetic energy, which we'll define in a bit. And when I put on my brakes, the kinetic energy of the car is turned into heat using the friction of the brakes. And so the total energy of the car and the brakes and the road and the atmosphere system is conserved, but the energy for the car alone is not conserved. Okay, it's reduced by the braking. So there's always some system. You can always find where that energy went to, but sometimes it can be tricky. So the definitions, the first one is kinetic energy. It's any object in motion has kinetic energy. And any object with velocity or mass has kinetic energy, and it's 1/2 mv squared. We use K for kinetic. More mass, more energy, more velocity, more energy. One thing we'll note here is that the units, so here is mass, it's kilogram, and then velocity squared will be meter squared over second squared. This is defined as the joule, and it'll be the unit for all of our energy quantities. Potential energy is a little bit more tricky. I think kinetic is pretty, most people get that right away. Potential is a little bit tricky. It's stored energy, and this thing is kind of weird here, but potential energy depends on the position or configuration of an object. And so our example is gravitational potential energy. The other one we'll talk about in a little bit is energy of a spring. Okay, potential energy is stored energy, and it depends on how whatever you're talking about is situated, how its position is or how its configuration is. We use the letter U for potential energy, and in this example here, the roller coaster's gravitational potential energy depends on its height above the ground. Now, to get a little more quantitative here, with gravitational potential energy, it's potential energy due to the Earth's gravitational field. It's an energy of position. And so, for example, we'll use here Yogi Bear, who's standing on a cliff of height y. And so he's got a mass m, and he's at a height y. And so we'll say that his gravitational potential energy, which we use U sub g, is mgy plus UGI, which is whatever the potential is down at the bottom of the cliff. Now, typically, what we'll do is we'll call that 0. You have the freedom to call the potential energy to be 0 at some point, and a lot of times you'll do it at the bottom of the cliff. And so the potential energy, gravitational potential energy for this Yogi the Bear is mgy. Thermal energy is the last form of energy we'll talk about today. We won't get too much into it. Basically, thermal energy is heat, transferred in and out of something. So here's a horseshoe. It's really hot. It's red hot. Thermal energy is the sum of the microscopic kinetic and potential energies of all the atoms in that object. So it's really just a combination of kinetic energies and potential energies that we've been talking about, but it's in some kind of an object. And so in our first example, the kinetic energy of the car was transferred into heat of the brake pads. And so thermal energy would be how that heat would be, how we would call that heat. And so the picture that the book likes to talk about is the basic energy model. And that's just this picture here where you have your system, and your system, which is what we talk about now. So for right now, we're talking mostly about our system. The system, you have energies that can be kinetic, potential, or thermal, which would be heating up or taking heat from something inside your system. And basically, the energy can be transferred back and forth. In our one example, the kinetic energy of the car went into thermal energy of a heat. Okay, but there'll be examples where potential energy will go into kinetic energy and vice versa. Again, energy isn't created or destroyed, it's just transferred from one form to another. Now, one thing that the book does is it starts here with just a simple kinematic rule. So the book, in sort of developing the equations and the math, what we're doing right now, start with simple kinematics from a couple of weeks ago. And so we have this equation here, which is one of our kinematics equations. And what we do is say, first of all, that the acceleration in the y direction is negative g. So we're going to assume there is no air resistance, no air friction. The only thing happening is just gravity is pulling down. And what we do is they just expand this out a little bit and rearrange it. And you notice that you get this situation where you got the left-hand side is final, the right-hand side is initial. So kind of like we have momentum, final equals initial. Then they multiply both sides at 1/2 times m, which is only because they know that it works out nicely. And you see that what happens is you get this term that's the same shape on both sides. Again, one side's the final, one side's the initial. What is it? It's the kinetic energy plus the gravitational potential energy. And so from kinematics, we see that this combination of kinetic plus potential is conserved. Okay, and we'll talk more about this. And so we can think about this kinematics equation in terms of energy. There's some insight here we have into conservation of energy. And so what we do is we say, okay, so kinetic energy and gravitational potential energy, the sum is not changed when an object is in free fall. Its initial and final values are equal. Here's what we have right over here. So when something is in free fall, okay, the sum of the kinetic plus the potential does not change. And now let's look at another example. And so we know when it's in free fall it doesn't change. What about if we have a box sliding down a frictionless surface? Okay, so here's the box, a blue box sliding down the frictionless inclined plane. So we take the same equation we had before. Now, if there is no friction, the acceleration, as we've talked about before, is negative g sine theta. All right, so now let's take some trigonometry here. So sine of theta is opposite over hypotenuse. The opposite is delta y. The hypotenuse is delta s. If I rearrange this, I get that delta s equals delta y over sine of theta. If I plug all this business in, what I notice here is that these sine thetas cancel, and I'm left with this exact same equation we just had. The sum of the kinetic plus the potential final equals the sum of the kinetic plus the gravitational potential initial. And so what this says is it doesn't matter if the block falls in free fall down this way or if it slides down this way. If there's no friction, okay, then the sum of the kinetic plus the potential does not change during this event. And so in other words, this equation we have works for any frictionless surface or any path that the object might take, is what we sort of get from this. And so we define what's called the mechanical energy, which is this sum of the kinetic plus the potential. All right, and we use this so much that we'll actually drop the mechanical part from it oftentimes, but it is important that it's the mechanical energy, okay, and it's the kinetic plus the potential. And so we say, and now this is a little bit tricky, we're going to be able to define this a little bit more concretely later, but for now we're just going to say that when only gravity is acting on an object, it conserves mechanical energy, or the mechanical energy stays the same. And so this equation that we've been dealing with, this is the equation here that we can use to help us solve for things. And again, it's when only gravity is acting, right? We could not involve friction before, either air friction or the friction of the incline. And so friction is not allowed, only gravity. And again, we'll talk about this more in depth later when we talk about work in chapter 11. And so here's a real basic example of this. Here's a bobsled going down. Now it's going down a frictionless ice surface, so there is no friction, so it conserves mechanical energy. You see here's the kinetic, and here's the potential, and basically it has a total of 600,000 joules, and that stays the same every time. And so what happens is initially it's got 6,000 of potential energy, all right, 600,000 rather, and it transfers some of that into kinetic. So right here it's transferred 200,000 over, it's got 400,000 left in its potential. Here it's got 400,000 kinetic, 200,000 in potential, and finally at the bottom it's got 0 potential, and it's all kinetic. And so it just changed from one form to another, but the total is 600,000 at any point. So a quick example here, we've got, again, Yogi Bear on this cliff. Suppose Yogi steps off the cliff which is a height y with 0 velocity initially. What will his speed be when he hits the water? What we do is we make the assumption that for Yogi Bear, the air friction, the air resistance is 0, and so it's negligible. We can forget about it, so we can conserve the mechanical energy. And so the final equals the initial. And so the sum of the kinetic plus the potential final equals the sum of the kinetic plus the potential initial. And so here I'll call the initial case when he just steps off, and the final case to be down there when he hits the water. And so we'll call his initial velocity 0. His final velocity I'll just call v, just because we're going to solve for that. And then his initial position will be y, and his final position will be 0. And so the trick with these kind of problems is setting up your initial and your final cases and what the values are. And so when I plug into my equation here, okay, it's 0 initial kinetic plus mgy is his potential energy initial, and afterwards he's got 0 potential energy. He hits the bottom, he's got height 0, and it's all in kinetic. So here is an example of Yogi starts with potential energy and that transfers into kinetic energy. Get rid of those zeros, and you notice here the mass cancels. So that's really interesting. Okay, we know this. Okay, we've been talking about this for a while. In kinematics equations, mass never came up. If you had a ball flying through the air, you didn't care what its mass was, and if you wanted to find what its what its velocity was going to be at some later time. And so here that cancels out. We solve for the velocity, and we get, sorry about that, you get radical 2g times y. Now the last thing is, how come Yogi no longer conserves mechanical energy when he hits the water? But when he hits the water, there'll be some force that's not gravity. Okay, friction is distinctly not allowed with this here, and so the water force would be kind of like a form of friction. But whatever, this equation we have, the conservation of mechanical energy is only true when gravity is the only thing acting for right now. We'll talk more about that later. So here we go. Give it a try problem. We have someone sliding down 4 frictionless slides, rank in order from largest to smallest, her speeds at the bottom. Okay, so this is a trick. One thing about the conservation of mechanical energy, so since it's frictionless, the only thing acting on this person going down the slide is going to be gravity. And so what's going to happen is, finally, the person's going to have kinetic energy of 1/2 mv final. Initially, they're going to have the gravitational potential of mgy, okay, or actually in this case, rather, since it's h, it would be mgh. All right, and so just like with the Yogi Bear example, when I solve for this, the answer will be 2g times h, and it doesn't matter what path they took because there's no friction. Okay, this is one of the powerful things about conservation of mechanical energy, is in this problem here, you know it has to be the same at the bottom for all 4 of them. And so it can save you a lot of time if you can figure out that it works. Again, the key is that there's no friction. Finally, with energy, we're going to talk about energy related to springs. And so here is the force due to a spring. So with a spring, what we like to talk about is, we like to talk about, for a spring has what I call its happy position. So if a spring is hanging out, okay, right here would be the place where it would be hanging out if there's nobody pushing or pulling on it. That's its equilibrium position, or its happy position. And so here, if I take my hand and push against the spring, okay, push this way, then the force of the spring is going to try to restore the spring to its happy point. And by other example, if I take my hand and pull it this way, so pull the spring, okay, the spring is going to have a force backwards, again trying to restore it to its happy point. So the spring force always opposes the force that you apply. Now, to make this into an equation, it'll look like this: negative k times delta s, where delta s is the distance the spring is compressed or stretched from its happy point. Okay, so if the spring is at its equilibrium position at its happy point, delta s will be 0, and then it's whatever distance it's been moved from that point. And k just tells you how strong the spring is. And so if you look at here, this negative sign has to be there because the negative sign sort of gives you this sense that the spring counters whatever you do to it. And so here in this case, okay, if I push the spring backwards, that's a negative delta S, and I get a positive spring force, which is what we expect. And then if my hand pulls it to the right, that's a positive delta S, and I get a negative spring force, just like we would expect. So the spring force is a restoring force. Like I said, it always works to restore the original position. And the K constant depends on many factors. But basically, it's a measure of how strong the spring is. So a really large K would be like a shock absorber in a car, very strong, and a small one would be like a slinky, pretty weak. Now, you might think, why are we spending so much time on springs? Why do we care? Well, it's true that springs, you don't maybe see them every day, but you see things that are like springs very often. Okay, and there's a lot of things. So here, basically, there's a list of a bunch of things that can behave like a spring. Okay, a pendulum behaves like a spring. If you perturb it, it bounces back and forth and tries to restore itself, just like a spring does. A basketball, if you press on the basketball, it tries to restore the basketball and has a force against you. The tendons in your arm behave like a spring. Okay, so many forces do this. Molecules, if you have two molecules that are bonded together, if you try to pull them apart, the force that keeps them together acts like a spring. So it's a very important force in physics, the spring-like restoring force is. Now, in a similar fashion, the textbook goes through, like we did on the previous slide, and gets us a new conservation of mechanical energy law for springs. And from this, we get the definition that the elastic potential energy, so the potential energy of a spring is like this. It's 1/2 the K constant times the distance it's perturbed from the happy point squared. And so it's a new piece, a new kind of potential energy. We have two now. We have gravitational and then spring-like or elastic potential. And so what we can do is now come up with a new sort of grand conservation of mechanical energy. Now again, this isn't 100% the best way to say this, but it's good when the only things that are acting in your problem are gravity or a spring-like force. And so you see here, we've basically got the same pieces we had last time, and now we just add in the fact that we have this possible 1/2 K x squared spring part. And so let's try an example here. So here what I've done is we've pushed the spring backwards. So in the initial case, we pushed the spring backwards, connected to some kind of a box. The box has a mass of 5 kilograms, and I've pushed the spring backwards 0.5 meters. We allow the spring to uncompress, and we want to know is how fast will the box be going afterwards. So give this a try, and we'll talk about it. Okay. I got 1 meters per second. So the key here is, first of all, is that mechanical energy is conserved. Okay, so mechanical energy is the key. And the reason is the table is frictionless. So there is no friction. The only thing that's acting here is a spring. All right, and so we take our equation, conservation of mechanical energy, and so here is the big long thing. Now actually, since gravity is not really doing anything, we can just cancel that out. And so it's all the spring force. And so what happens is initially, so x initial is that, I think it was 0.5 meters or something. X final is going to be 0, so that cancels out. And the block is not moving initially, so that cancels out. So what we have then is we're going to have 1/2 mv squared plus 1/2 kx squared. The 1/2s will cancel, and we go through and solve for our velocity, and you get this thing here. And when you plug in the special numbers you had, it comes to be 1 meter per second. Again, the trick is that there was no friction acting, and so what's happening here is basically initially, okay, the spring had a bunch of potential energy. It was all ready to shoot out, and afterwards that energy got converted into kinetic energy. And now this equation allowed us to actually solve for the number. But the point is that you have energy in one form being transferred to another.